Hello mathematicians, I just wanted to share with you a few thoughts, and they'll be pretty random, about getting the most out of the effort that you're putting in for maths. I've said to you before that I'm constantly amazed at how far you've come, and it's sounding a little bit like a broken record, I suppose, to you. But the reason is that you have learnt so much maths in the last 12 months, but we've still got work to do on you actually taking that maths and organising it and applying it. So a lot of what I think we have problems with is about how you pack the information into your brain. And no doubt it's impossible not to be influenced by how you've been doing it for years in the past. But I think we need to be a little bit self-questioning about what we are trying to arrange in our brain and think about our methods. So I guess because you have so much to learn right across your range of subjects, you need to really check what it is that you are committing to memory or trying to commit to memory. Does it have to be committed to memory, or does it have to be understood, and the committing to memory part will generally take care of itself then? So you need to know what it is that you're working on, and that includes the reason that I say to you, you need to do your homework with a purpose. Why are we doing this particular thing? Really, it's easier to store and it's easier to retrieve if you know how it connects to the rest. So that when you need the information in a hurry and you're not sure perhaps even exactly which bit of information it is, if you've got some set of connections, your brain tends to draw those out in a package. And then you've got a chance of sifting through that little sample and making your best choice about what you need. It also helps sometimes just to daydream. We know that we dream at night to process experiences. When you daydream and think about what if, wonder about things, even if it seems like you're not being productive, if you are thinking purely about different applications, different consequences, different combinations, different meanings, different interpretations, then that can help, again, encode and arrange the material in your brain. Now, these tips are not just for maths, they work for anything. So they're just a way of putting information into appropriate spots. You've probably heard that old saying, it's not exactly true, that neurons that fire together grow together. We make new neural pathways. And that's what you are basically in the process of doing. You're shaping your brain to reflect what it needs to know for the HSC, and then you'll reshape it for something else. So assuming we have our brain packed, then once we've got it encoded in a meaningful way, the big issue then is how do we get it back out so that we can use that information for problem solving. I've already mentioned that if you've got it in there in basically a chain of connections, one bit will sort of trigger the next bit and so on. For example, you can't think about food, perhaps, without thinking about the foods that you really like or the foods that you really dislike. This, unfortunately, is what happens when you start to stress. So your nicely packed brain becomes a jumble, and you know what it's like trying to retrieve information from a jumble. So we do have to work on reducing our stress, and that's not an easy task. But reducing your stress can be partially managed if you know that you can recover the information in a meaningful way. And if you've got a technique for recovering it and a technique for applying it to problem solving. So this is another aspect that I think we need to look at. When we problem solve in maths, or again, anything else for that matter, what we have to do first of all, before we can go any further, is to understand the problem. We have to answer the question as it's written, not as we would like it to be written or as we think it should be written, but actually as it's written. And once we understand the problem, then we won't be able to help almost being able to think about which of the considerable range of tools you have, mathematical tools, are going to be the ones which might be applicable to this job. You mightn't be able to drag out the correct one or two straight up, but you'll know, like you grab a handful of tools and then you'll refine it. And that refinement comes about in the plan that you set up. So you have a vague idea about where you want to go. You should have a good idea about where you are, so that's the understanding of the problem. And then you start to follow that plan. So you actually start to do stuff. It's very hard to solve a maths problem without a pencil in your hand and be writing stuff down. Then you check your progress. You check every step of the way, whether you're on the right track, whether you are indeed doing what you intended to do, whether your answers make sense, and right at the very end you keep doing that checking as well. So it's a feedback loop. And by the time we've gone through that, hopefully we're at least nearer to the solution of the problem. Occasionally you might just miss that flash of insight that you need, but hopefully being well prepared will get you further. Again, while the cliches are flowing, the chance favours the prepared mind. You prepare your mind and hopefully that insight will come. So how do we go about doing all of this sorting in your head? I think summaries are where we have to start. I'm not sure how you do summaries based on your junior school experience, but I would say to you that when you do your summaries, it really is just the main ideas. So you shouldn't have more than a page per topic. Now, if you think, well, I can't possibly shrink it down to a page, then that becomes, in a way, your challenge. You've got to go through and see what is really the key stuff, what's vital, what can you not do without, and that's what has to go into your summary. So even the process of paring back the amount of content that you've got means that you have to read it, you have to think about connections, you have to see whether something is included in something else, so that it becomes really just the big ideas. Preferably not just text. And I know this is really a personal taste thing, but a page of text is really hard to commit to memory. It doesn't give your brain much to work with. Our brain has evolved to work with shapes and colours. That's just who we are. So if we can work with shapes and colours, even if it's as little as changing the colour of your text. We also know that maths is so often about graphs, which are just diagrams. And we also want to know connections. So mind mapping is ideal, but you don't have to do hard and fast mind mapping. Just something which is going to make the information organised and memorable. Now there's another little thing that I think is worth pursuing as well. And you can only do this when you have some time, which is why I would suggest through these holidays. And that is to just make webs of connections and start with a word and see where it takes you. And decide you're going to give yourself 5 minutes, 10 minutes, 2 minutes to make this web. And you won't cover everything, you won't bind everything together, but it's a starting point. So you might, once you do this web, it's not definitive. You screw it up and throw it away. Summaries are pretty much like that, but they're a bit more of a work. But these little webs, you do them, and it's the doing them which is the study. So if I was doing one on differentiation, for example, and I gave myself 5 minutes to do something about it, I might consider what is differentiation, how do we differentiate, and why do we differentiate? And there's nothing special about those three. So anything which basically gives you a starter, and they're just starter words. So what is differentiation? Again, paired back to its essentials. Differentiation is about finding the slope of a curve. So if we have y equals f of x as the curve, then when we differentiate and we get dy dx, or y dashed, or f dashed of x, so we don't have to write them down, but we know that they're all the same. All of those things are actually slope functions or slope equations. And if we want the slope of a curve at a particular spot, just like if we wanted the y value at a particular spot, we put it into y equals f of x. Then if we want the slope at a particular spot, we put it into y dashed or f dashed of x. How do we do it? Well, this is the mechanics. So up here we've got our basic differential, something raised to a power, bring the power down and subtract 1. We've got the beginnings of the chain rule, so I'm not writing the chain rule out for you, you've got that. We have the product rule, if we've got two things which depend on x, which are multiplied. We've got the quotient rule, and we've added what happens if the function you happen to be working with is a function that you're taking a log of. And we know that there's a special rule for that. Y dashed is f dashed of x over f of x. Now we'll have a few more of those to add by the time we finish the course, but not much more. Probably about 3 more lines and that would be it. So writing them down doesn't mean that you know how they work. You then, if need be, go back and check how each of these works. But you've got to know they're there before you can work with them. And you have to know when you've got a product, when you've got a chain rule, when you've got a quotient rule, etc. Now, why do we differentiate? Well, we said up there in a sense for the slope of the curve, but what sort of questions, perhaps? Well, they're often to do with tangents. So getting equations of tangents and normals, finding where they intersect axes, other curves and so on. But basically, related to differentiation, we just want to recognise that the slope of the straight line, which is what a tangent is, at a particular point is f dashed of x at that particular point. And we also use it for curve sketching. So with curves, we know that the points of interest are where it's going up, where it's coming down, where it's not doing either, where it's stopping going up and starting coming down and so on. And they're all described by differentiation. So here we can see that at the very top up here, we've got a spot where y dashed equals 0. And in this particular case, what distinguishes it from this one down here, where y dashed equals 0, is that y double dashed is a negative. This curve is concave down to give a maximum. This one is concave up to give a minimum. It stops being concave one way and going another when just the second differential is 0, but not the first differential, because clearly the slope is not horizontal there. It's horizontal here, and we are changing concavity as well. So the first and the second differential are 0, so this is a possible horizontal point of inflection. The only way to make certain is really to test the sign of the slope either side, and if it's positive there and positive there, then what we've got is definitely a point of inflection. We also know that this is what an increasing function is, and over here we've got a decreasing function. And we also know, and you've known for a long time, what it is that makes a x-intercept, it's where y equals 0. So all of these little things have to be known really well, packaged away in some sort of order, so that you can retrieve them as needed. If you want some clues about things that you could build webs around, these are some, but it's not an exhaustive list, it's not even a great list. So you could start with any of these words and then just connect as many ideas as you could within a set time limit. So let's go back to problem solving now. So this was our problem solving strategy. So if we apply that to a particular problem, so this was a differentiation question essentially, one connected with differentiation of the 2018 HSC. So step 1, as we saw in the plan, is understand the problem. So we consider that curve. Now that particular curve is a cubic for what it's worth. We've got a vague idea of cubics. We know it could have up to 2 bumps, or it might have no bumps. We also, I hope, almost can't look at that without wanting to do that, which tells us that we're going to cut the axis at 0 and at 6. And then we look at what it wants us to do. Find the stationary points and determine their nature. So what's that going to say, or what tools does that say we require? So stationary points we know. Y dashed is 0, y double dashed is what determines their nature. The second line says, or part of the problem says, given that this point lies on the curve. Now again, it's got nothing to do with the question, but I hope your brain says, oh, that means if x equals 2, when I put 2 into this equation up here, I would get y equals 16. But given that that lies on the curve, show that it's a point of inflection. So a point of inflection is where the second differential only is 0, not the first differential. And the last part is to sketch the curve. So we've got a vague idea of the tools. We've got the basis of a plan, because once we've got the tools out, basically it's using those tools to answer the question, and that's our plan. And then we do it and we check it. Sketch the curve, find the x and the y intercepts, so we know how to do those. And sketching the curve is just going to involve putting together the bits from the previous information. So let's move on. First part. So if we have the curves equation, then we get the first differential. We know how to do that. We know that the first differential is 0 if we've got a stationary point. So that means that this is 0. We know how to factorise, and we get 2 stationary points. Now before we go any further, does that fit with the fact that we've got a cubic? So this is a check. Yes, it does, because a cubic could have up to 2 bumps. So we know we're within the realms of possibility. If we got 3 bumps, we've done something wrong. If we got 1 bump, we're not sure. But it also said up here, so we keep checking back to the question, find the stationary point. It didn't say what are the x values, so that means we need the y value. So we go to our original equation and we plug x equals 0 and x equals 4 into that. So we're checking, it all seems good so far. You probably have a feeling that 0, 0 will be a minimum and this will be a maximum, just from your common sense, knowing that you've got these 2 points. But we need proof of that. So now we want to work on the nature of the turning points. So we get our second differential. We know how to do that. Then for each of our stationary points, we check the second differential. Now it turned out to be a positive, which indicates that we've got a minimum turning point, and a negative, which indicates we've got a maximum. So we're happy with that because it fits our preconceptions, if you like. Then, second part, given that that point is on the curve, show it's a point of inflection. So we had our plan for this. When x equals 2, we find that y double dash, now if this was an exam I probably would have written y double dashed equals 12 minus 6 by 2, which equals 0. And also y dashed is not equal to 0. And there are our conditions for this to be a point of inflection. So we're there, we've done that. And that's 5 marks so far, 10 minutes work. Hopefully we've got 5 marks and we've picked up a little bit of time. Now to sketch the curve, showing the stationary points, the point of inflection, so we've got all of that stuff, and the x and y intercepts. So we start a sketch, use a ruler if you can, don't be like me. Find where it cuts the x-axis, which is when y equals 0, so that will be at 0 and 6. We don't have to, well, I didn't write down, we cut the y-axis when x equals 0, because when x equals 0, that's going to give us 0. So that point, our minimum turning point, is in fact where we cut the y-axis. It's the only spot. So mark all the others, so where we cut through the x-axis, our maximum and our minimum, our point of inflection where concavity changes, and then just draw a curve through them. Okay, so I'll leave you with that long video, but I think it's important. I wouldn't have bothered otherwise. This is where we need to put our effort, as much into solving the maths problems as doing the maths questions, as learning the maths concepts, sorry. Doing the homework is to help you encode, as well as to prepare you for the questions and polish up your toolkit, and to make retrieval of information relatively automatic. Thanks everybody, have a great break, do what you can over the holidays, but get some rest time in as well.